Chapter 3, Lesson 5 of Pre-Calculus, we're going to look at solving these exponential equations. Now remember, there's two things that I want you to remember, is that when we're solving an equation, the first thing we always have to think about is we have to isolate the term that has the exponent in it, or the variable, excuse me, in it. And then once that term with the variable is isolated, we then undo, or we do the inverse operation to actually then finish solving off for the variable. Now remember, as we've been talking about, if we begin with an exponential, we isolate it, and what undoes an exponential? A logarithm. So the inverse operation that we're going to do at the end is to take the logarithm of both sides. If we begin with a logarithmic equation, then we're going to do the inverse, we'll do the exponential. That will be in the next video. So I have the answers here because when you're doing these exponential equations, most often the answer is going to end up being a decimal. So I will do the steps, show you the algebra of it, and then you can check out the examples or check out calculate the answer for yourself and see that we do have it right. So we'll kind of go from there. All right, I have to do one thing here. I've got to get my board set up here, so let me do that. Okay, now we're ready. All right, so in our first example here, 14 to the b is equal to 28. The term b, or the term with the variable, is already isolated, so I simply have to undo the operation. So to undo this exponential, we're going to take the logarithm of both sides. So we're going to take the log of 14b, 14 to the b, and just like any other operation or equation solving property that we use, we have to do the same thing to both sides. So taking the logarithm of both sides is the inverse, or it's going to undo this exponential operation that's going on here. We then apply the power property, and we put the b in front, so this becomes b times the log of 14 equals the log of 28. So remember, this is b times, this is one term. So to undo now this multiplication, b times this, we divide by the log of 14 on both sides. So the b is going to be equal to the log of 28 divided by the log of 14. Now, if you enter that in your calculator, you'll get this decimal approximation here. Now, it says to round off to the nearest 10 thousandths. That's 4 decimal places, so that's what we'll do. Okay, so the isolated exponential term, you take the logarithm of both sides, then you apply the power property, moving that in front, and then you have this b times this, and then you just simply solve for b by undoing that operation. Okay, all right, number 2 here then. 13 to the m is equal to 77. Again, the term that has the variable I'm solving for is already by itself, so I just undo that by taking the log of both sides. Remember, we're taking the log of both sides. Then we apply the power property, moving that exponent into the front. Okay, and then this is m times that, so I can divide by the log of 13, so the log of 77 divided by the log of 13, that's your exact answer. And then again, if you calculate that, that should give you your approximated answer there. Okay, I'm not going to check these, so if I happen to do something wrong, I'm not checking those, and you notice that, then email me and I'll make sure I come back and change it, but hopefully I can get these right. I might check one or two as we go down the road, but I'm probably not going to do that. Okay, so let's go to another example. I think we'll go down here to number, we'll just go right through it. We'll go to number 3 next. All right, so let me move that up here. All right. Okay, so for number 3, again, our term with the variable is already isolated, so I'm simply going to take the log, or undo that exponential by taking the log of both sides. We then apply the power property, so that's p. I'm going to do this just so you kind of see. Log of 10 equals log of 65, and then that's multiplication. So p is going to be equal to the log of 65, then divided by the log of 10. So this is my exact answer, and this should be the decimal equivalent. Okay. Now moving over here to number 4 is very important, a very important concept. You'll notice that we do have our isolated variable, and remember, e is not a variable, e is a number. And so we have a number raised to this power. Now, because this is a base e, we don't want to take the log. You'll notice we were taking the log. This is actually the common log, you'll notice, because we didn't write the base 10. So because we have a natural base here, we're going to take the natural log then of both sides in order to solve this. So the natural log, because we have a base e. Now, this is, if you think about this, if we just took this over here, e to the n, this is a property we had earlier that we talked about. If I was to evaluate this log, remember, what does this mean? What is the exponent of e? That's what this word, remember, our base is e. What is the exponent of e that will give me e to the n? Well, it's just simply n. So whenever you take the natural log of a base e number, that's always going to simplify to the exponent. So this simplified is simply n. So n is equal to the natural log of 75. So you'll notice there's kind of a step that we can skip there. Now, we could go through the process and end up with the same answer, but that's a little bit of a shortcut here. We could apply the power property, natural log of e equals natural log 75, and then divide by 75 natural log of e. But the natural log of e to what power will give me e? Well, e to be the first power. This simplifies to a 1, which ends up being this. All right. So you can take this little shortcut by realizing that when you take the natural log of e to a power, it's going to simplify to a power. That's that property. Or if you take the long way around, you'll end up in the same place, but that's a little shortcut you might want to be aware of. Okay. Let's do some more examples. Okay, example 5 here. The term that has the variable is already isolated, so to undo the exponential, we're going to take the log of both sides, equals log of 53. We then apply the power property, so that's log of 53. And then we divide by log of 8, so this is equal to log of 53, then divided by log of 8. And again, this would be our exact answer. This would be the decimal approximate. In our next few examples, it's going to get a little bit more difficult, but again, we're going to do the same thing. We're going to identify the term that has the variable, we're going to isolate it, and then we're going to undo it by using logarithms. So in this example number 6 here, we notice here's the term that has the variable I'm solving for, r. R is part of the exponent. So this has to be by itself first. So I'm going to divide both sides by a -9. So that's going to give me 73 over 9 on this side. Now please don't give me a decimal approximation, just leave it like that. Okay? And again, it's positive because we have a negative divided by a negative. Well, now that we have this isolated, now we can undo this exponential item or exponential operation by doing the inverse. So we're going to take the log of both sides. So we're going to take the log of 12 to the r minus 3 equals, now be careful here, you're going to again keep this together. This is a single number. Now again, I don't want you to multiply this out or calculate it out because it's all going to be a decimal approximate, and then we're going to use it again. It's going to make this answer a little bit further off if we start using estimated numbers way up here in the first step. Alright, now here's the exponent r minus 3. Now be careful because that all goes together. R minus 3 is going to go in front using this property, power property, equals a log of 73 over 9. Now this times this, so I'm going to divide by log of 12. So I'm going to have r minus 3 is equal to, now here's where again it gets kind of tricky, but you have to be careful. That's one number divided by now this log of 12. And then we're solving for r, so we're going to add 3 to both sides. So this ends up being the log of 73 over 9 divided by the log of 12, that's one whole number, plus 3. So here would be my exact answer if I were to leave it, if I was not able to use a calculator in a test situation or something like that. So that's my exact answer. So when we calculate that, we should get this. So I'm going to go ahead and calculate that on my calculator just to double check because that one's got a lot going on. Now, it's kind of difficult to get all of this entered into my calculator using getting all of the parentheses in the right place. So what I usually like to do is I do each one of these one at a time. So I'm going to take the log of the numerator. So I do log, and then it gives me a parenthesis. So 73 divided by 9, and I push enter. That gives me an estimated number. Now I don't write that number down. The calculator is going to use that. So then I divide that number. So I hit divided by, and then I do log 12, and I push enter. And then all of that is plus 3, so I get plus 3, and I get 3.8424 rounded, so I did get the answer, okay? So again, that's the algebra behind it, and again, it looks kind of complicated, but you just have to remember you have to keep these fractions together, and remember that this goes together, and then just be careful as you're moving these things around. And again, you don't want to use decimal approximate. If I took the decimal approximate up here at 73 divided by 9, and then I took the logarithm here and took the decimal approximate of that, and then I divided that by this decimal approximate, by the time I got down to here, this number is going to be a bit further off, and I'm not going to get 3.8424. I'll get something close, but it's not going to be quite as exact or quite this number, because I've been using estimated numbers all the way back here from step 1. Okay, I'll do a number of more examples again. We're going to go through this, so you watch as many as you need, and hopefully these will all be helpful for you. Okay, in our next example, again, we notice we identify where our term is with the variable, and we need to isolate that first. So we're going to need to subtract 1 from both sides. 13 to the negative 4v is equal to 1. And then once this is isolated, we can go ahead and apply the log, or undo it by taking the log of both sides. So this is the log of 13 to the negative 4v is equal to the log of 1. All right, and then we're going to move this over in front. And I'll just put that, so you see that's multiplication, equals the log of 1. And then say negative 4v is equal to log of 1 divided by log of 13. And then now again, you have to be careful here, because we're going to divide by negative 4. So v is going to be equal to, now my numerator is log of 1 over log of 13, and then that's being divided by this negative 4 at the end. So this would be, again, my exact answer, and then we should calculate that out and get this. Again, I'm going to calculate this just to make sure. So I've got log of 1. I'm going to push enter. That's 0. So I really don't have to go any further, because that's a 0. So log of 1 is 0. 0 divided by this log is still going to be 0. And then that 0 divided by this is still going to be 0. So I end up being 0. So actually, if I recognize it right up here that this is actually equal to 0, and again, this means what's the exponent of this base that gives me 13 to the negative 4? Well, because it's 0, it's going to be 0 all the way through. So the answer is 0. Okay? Let's go ahead and do this next example. So first thing I want to do is identify the term with the variable that I'm solving for, which is this one, and I want to isolate it. So I'm going to have to subtract 5 from both sides. So I'm going to have 15 to the negative 9a is equal to 63 minus 5, which is what? 58. 8, 9, 60, 1, 2, 3. Okay, double check. Okay, then I need to, now that I have this term by itself, I need to undo exponential. Logarithm undoes exponential. So we're going to take log 15 negative 9a is equal to log 58. I apply the power property, put 9a out here in front, times log of 15 is equal to log of 58. Then I'm going to, again, I'm solving for a, so this has to be isolated, so I'm going to divide by log of 15 divided by log of 15. Now remember, this is one number, so in my last step, when I'm dividing by negative 9, I'm taking this log of 58 divided by this log of 15, whatever that number is, and I'm dividing that by negative 9, and that's going to give me my answer. So again, I'll walk you through this. We're going to do log of 58, enter. We're going to divide that by log 15, enter, and we're going to divide that by negative 9, enter, and it's going to give me negative 1.6659, which rounds off to negative 1.666. Okay? All right, I'm going to do some more examples, so if you think you got it, great. If not, I will do one that's a little bit more challenging, so if you want to keep watching and look for that one, you can do that one. Taking a look at number 11 here, this gets a little bit more complicated, but if we follow what we've been doing all along, we'll be okay. Now again, we have to identify which term has the variable that we're solving for. Now you have to be careful here because e is a number, and so the term that has the variable is this e to the 6x minus 5. Now the negative 2 does not have that exponent to it. So this is the term that needs to be isolated. So we're going to need to subtract 5 to both sides, and then divide by this negative 2 in order to isolate this e to the 6x minus 5. Okay, so we're going to subtract 5 from both sides first. So this is minus 5 is equal to negative 90.5. All right, and then we're going to divide by negative 2 because, again, what I'm trying to isolate is this term right here. So it still has this being multiplied by negative 2. So we're going to have e to the 6x minus 5 then is equal to this negative divided by negative, so it's going to be positive. And 90.5 divided by 2 comes out to be 45.25. Okay? Now that we have this term isolated, we can undo this exponent by taking a logarithm. But because the base is a base e, we're going to take the natural log of both sides. So we're going to take the natural log of e to the 6x minus 5. And then we're also going to have to take the natural log of this 45.25. Now remember what we talked about before. When we take the natural log of an e number, of an e base, it simplifies to this 6x minus 5. Again, if you go back to evaluating logarithms, this means what's the exponent of the base e, what's the exponent of e that will give me e to the 6x minus 5? Well, the exponent that will give me e to the 6x minus 5 is 6x minus 5. So that equals the natural log then of 45.25. And again, don't be calculating this here because it's going to be an estimated number. It's going to be off if we do it here. So now here's the term with the variable. So we're going to isolate that by adding 5. So the natural log of 45.25 is going to be added to by 5. And then we're going to divide this whole side by 6. So the natural log of 45.25, that number, we're going to add 5 to it, and then we're going to divide by 6. So this would be my exact answer, and if we calculate that, that does come out to be this number here. Okay, let's go ahead and do number 12 over here. Now again, we have to identify the variable and the term that has it that we're solving for. So here's the term that has the variable, so that's the one that has to be isolated. So we're going to need to add 10, and we're going to need to get rid of this negative 3 as well. So we're going to have negative 3 e to the 2p plus 1. We're going to add 10 to both sides, so that's going to give me negative 72.9. And then we're going to, or I wrote that wrong. I said it right, I think, but I wrote it wrong. Negative 72.9. Then again, the term I'm trying to get by itself is right here, so I'm going to divide by negative 3. So e to the 2p plus 1 is going to be equal to this. Negative number divided by negative number is going to be positive. And again, I'm not going to divide it out because if it's an approximate number, I don't want an approximate number, I'll leave it exact. Now that this term is isolated, we can undo this exponential by taking the logarithm. Again, it's base e, so I'm going to take the natural log of both sides. So e, natural log of e to the 2p plus 1. And again, I'm going to take the natural log, and again, remember this 72.9 is a single number, but we're going to leave it like this. Now remember, this simplifies because we're taking a natural log of base e. It's going to simplify to the exponent. So this is going to be, again, still 72.9 divided by 3. And now here's the term with the variable, so I'm going to isolate it. 2p is equal to the natural log of 72.9 divided by 3, and we're subtracting 1 from both sides. And then we're going to divide by 2. So this would be the natural log of 72.9 over 3, that number minus 1, and then all of that divided by 2. So this would be my exact answer, and this is the decimal equivalent rounded off to 4 decimal places. So let's go ahead and calculate that just real quick. So I'm going to take the natural log of 72.9 and divide it by 3, enter. I'm going to take that number and subtract 1, enter. And I'm going to take that number, divide by 2, enter, and I get 1.0952, which is what I have my decimal approximation here. Okay, so again, be essentially the same. We're going to isolate the term that has the variable in it, and then we're going to undo it by taking the logarithm of both sides. All right, I think I'll do one more example. Let me look at these last few here, see which one's complicated, and then we'll wrap this up. Let's see. All right, so let's do number 15 then as our final example. So here we have, again, the term that has the variable we're solving for is right here. So this is going to have to be isolated. So we're going to have to move the 8 and take care of the 9 as well. So we're going to subtract 9 from both sides. So this is going to be negative 9 e, that one kind of messed up on me, e to the 10x plus 8.4, that's the exponent, equals, we're subtracting 8 from both sides, so that's going to be negative 11. Then again, here's the term that we're trying to isolate, so we're going to have to divide by this negative 9. So we're going to have e to the 10x plus 8.4 is equal to a negative again divided by a negative's a positive, so this is going to be 11 divided by 9. Now again, don't give me a decimal approximation here, you're going to be off at the end. So now that we have this by itself, we can undo the exponent by doing logarithms. So we're going to take the natural log of both sides. Now remember, when I take the natural log of this side, it's going to simplify to this, so I'm going to go ahead and do that in one step. So this is going to end up being 10x to the 8.4 when I take the natural log of this side, but then I also have to take the natural log of this side. So we have this. So now here's the variable. I need to isolate it, so I'm going to subtract 8.4. So we're going to have 10x is equal to the natural log of 11 over 9, and subtract 8.4, and then we're going to divide by 10. So x is the natural log of 11 ninths minus 8.4, and all of that's going to be divided by 10. This is my exact answer, and this should be the decimal approximate. So we'll go ahead and check that out. So natural log 11 divided by 9, and I'll do enter, minus, I'll take that 8.4, enter, and then we're going to divide that by 10, so it's negative 0.8199, and that is correct. All right. Actually, I said that was going to be the last one, but I'm going to do one more because I really like doing these once we get into them. Sorry, that's just the way I am. All right, so we'll just do number 16 here. So again, the term I'm trying to isolate, or the term that has my variable, is right here, so I'm going to isolate that one. 10e to the 10 minus 5m, and I'm going to add 7 to both sides, so that's going to be 51. Now this is going to be e to the 10, again, this is what I'm trying to isolate, so I'm going to divide by 10. So e to the 10 minus 5m. Now 51 divided by 10, it comes out even, a 5.1, so I'm going to go ahead and do that. And then again, I take the natural log of both sides, and that's going to simplify to 10 minus 5m when I take the natural log of this side. But again, I have to take the natural log of this side. And now here is my term that I'm isolating. So I'm going to subtract 10 from both sides. Is a natural log of 5.1 minus 10. And then I'm going to divide by negative 5. So m is equal to the natural log of 5.1 minus 10 divided by negative 5. So let's calculate that. So natural log of 5.1 is enter. I'm going to subtract 10 from that, enter. And I'm going to divide that by negative 5, enter. And that's going to be a positive 1.6742. So my exact answer and my decimal answer. Okay, so hopefully those were helpful. In the next video, we'll take a look at logarithms and how we, beginning with a logarithm equation, we use the inverse or the exponential to solve those.